Okay, so I'm going to give you a little insight into what the midterm exam is going to look like, what it's going to be about. Covers all the lecture material that we've had so far, but I'm going to try to just hit those big sort of high points that I would use to make test questions. So remote sensing. If I ask you what it is, you should know it's the art and science of obtaining information from data acquired at a distance. How that whole process works. Sunlight comes down, hits stuff, some gets absorbed, some passes through, some bounces off. We collect it with something. And we use different things to figure out what that is. Why? Gives us a lot of spatial information, scale specific, global, regional, local. It's objective and consistent, and it's detailed. Allows us to look at things like historical record and change detection for things like urban growth and flooding and historical pollution. All kinds of ways we can examine what is or is not going on. So how does it work? You have to have a source of energy, you have to have a target, and you have to have a sensor. And then you have this path length, which is the sort of distance that stuff has to travel through. You need to understand a little bit about the science of how light works. Energy sources and radiation principles, in other words, light speed is equal to the frequency times the wavelength. The frequency is the number of humps over a given distance, and the wavelength is the distance between the humps. So speed of light is equal to the particular wavelength times particular frequency. Most common units we use is a micrometer, which is 1 times 10 to the negative 6. And we typically label the spectrum with descriptive terms. So here's the spectrum. I would strongly advise you to know these in order, from the shortest wavelength, cosmic, to gamma, to X-ray, to ultraviolet, to blue, to green, to red, to near infrared, to mid infrared, to thermal infrared, to microwave, to TV and radio. My computer's being really annoying now. Don't advance the slides. There we go. Zoom in, you can see the visible spectrum. It's a very narrow part of the entire spectrum. But it's what we can see from about 0.4 to 0.7 micrometers. And we can see the blue, the green, and the red. 4 to 5, 5 to 6, 6 to 7. Know these numbers, know these things. Solar energy covers a whole lot of stuff. Ultraviolet, visible, near, and thermal. Alright, so characteristics of electromagnetic spectrum. It's easy to explain it with wave theory. It interacts with matter. Best explained by particle theory. So the electromagnetic energy is composed of discrete units. We call them photons or quanta. And so the energy of a quanta is explained by Planck's constant. I'm not going to ask you anything about that. Or how to solve it. But just remember that anything that is above absolute zero will emit some electromagnetic radiation. Terrestrial objects have a very different magnitude in terms of what they reflect or emit compared to things like the sun. But everything displaces something, emits something. Energy emitted varies with temperature. They call this Wien's displacement law. Think of heating up an iron bar. The hotter it gets, the more energy comes off of it, and it changes color. Now what a black body is, perfect radiator. Think of it as an energy battery. It radiates 100% of everything that comes into it. On the energy of incidence comes back off of it. Nothing's lost, nothing's absorbed, nothing is transmitted through it. What does it mean in remote sensing? Active systems versus passive systems. Active, we supply the energy. and we sense what is absorbed or reflected. In a passive system, we rely on outside sources like the sun, and we measure what is absorbed or reflected. Path length. It's a distance through the atmosphere that the energy has to go through. The effect varies depending on the sensor and the electromagnetic frequency that we're measuring, because some are not impacted at all or very minimally by the atmosphere, and others have significant issue with going through the atmosphere. 3 types of scattering: Rayleigh, Mie, and non-selective. Rayleigh makes the sky blue because short waves get more scattered. Mie is caused by water, vapor, and dust. Only the longer wavelengths are the ones that primarily get affected, and so it can be pretty pronounced in overcast conditions. Then there's non-selective, and this is what happens when particles that cause the scattering are much larger than the wavelength of what happens. And this example would be like light hitting clouds, and the cloud is looking white because the white is reflecting all the energy. Absorption results in the loss of energy in the atmosphere. Water vapor, CO2, ozone all have the ability to absorb energy. Remote sensing systems have to be designed to address this, because things that are affected by water vapor, CO2, and ozone, it's really hard to measure when you're with a satellite. So you've got to think about what you're trying to measure and how. This is a diagram that if I were to give you, you should be able to explain. One on the top shows the sun energy and the earth's energy. And you can see that the earth's energy is not really anything that we can see. Whereas right in the middle of the sun's is where the, believe it or not, visible light comes from. Second graph down shows transmission. And so the higher up the white goes, the more the energy that makes it through the atmosphere, and the less that is blocked. So white there in that 2 lines is the blue, green, and red. And other places where you see those little spikes of white approaching the top are called atmospheric windows, and there are certain frequencies that you can measure in those windows. In other situations, like when you get up around 100, you see that almost above 100 for a ways, there's nothing that is available, and that is completely blocked by the atmosphere. The bottom image shows you where certain sensors react along the spectrum, like the MNI, right along visible light, photography, going a little bit further in both directions, multispectral scanners covering a whole bunch more, and thermal scanners operating up in the infrared range, well, the thermal infrared range. So again, sun's energy, earth's energy. Big difference. Atmospheric windows where things get allowed through, like in the visible spectrum. Other places where things get completely blocked, like above 100. Talk about spectral reflectance. It's the energy of the wavelength reflected from the object divided by the energy of the wavelength of incidence upon the object. And it's a percentage, is all it amounts to. Spectral reflectance is a percent. So you look at a certain range of electromagnetic frequency, 100% hits, 20% is reflected, or 100 units hits, 20 units is reflected. It comes out to 20%. If I ask you to explain the energy of incidence and the associated fate of it, you should be able to tell me that the energy comes from some source, whether it's passive or active. It hits a target. Upon hitting the target, some is absorbed by the target, some is transmitted through the target, some is reflected from the target. Same thing we're talking about here. Different targets respond differently, and so you can use this to look at things and find interesting and cool stuff. like how pine trees and maple trees have different reflectances at different wavelengths, particularly in the near infrared, because cell structure and the amount of water that's contained and all that varies differently, and it causes it to have a uniquely different signature. So when you look with infrared, you can literally see where the pine trees are versus where the other trees are. We call this spectral signatures. A signature implies it's a unique spectral relationship. That might be a bit much. It's biogeochemical signatures, in other words, minerals or nitrogen in plants and stuff from hyperspectral data. We just kind of look at how this responds to what's going on. But there's a lot of variability. The spectra are not unique. Other things respond similarly. Illumination is not always constant. There's natural variation in the composition. Sensors are typically using things like mixed pixels because of the other things that we're looking at, and there's also a lot of just background noise that can be occurring in all of this. But we can use this to our advantage in a lot of different ways. For example, we can separate soil from vegetation, clouds from snow, dead plants from living ones. We can detect water stress in plants as well as nutrient deficiencies, and these are some examples that would show that. And just to talk about it here a little bit, you can see how dry grass and green grass have a different signature, as does soil, and there's certain places in the frequency where you can tell that the soil is less than the dry grass, and other places it's about the same. And you can use these things to your advantages. Same way with whether something's concrete, asphalt, or sand, water, snow, or clouds. So spectral reflectance of Earth features, what are some of the important ones? Chlorophyll at 0.45 to 0.67. Near infrared is useful for identifying changes in plant species because of this. There's also the water absorption bands at 1.4, 1.9, and 2.7. Snow absorbs more in the mid-infrared than clouds. Above 1.4, you can tell if it's snow or clouds. Here we've got water with a high dissolved oxygen, and water that's got a lot of chlorophyll. In other words, it's got a lot of vegetation in it, and it has very different signatures. The atmosphere can also have an impact on these patterns because there's things in that path length that can cause different stuff to change. So when you look at things on the surface and you look from a satellite, doesn't always pan out the same. Geometry can also have some impact on it. The angle that you're looking at things changes the size, changes the shape, can also change some of the responses. Here is a nice illustration of the spectral reflectance of vegetation and how it behaves, and you can also see where the three atmospheric water absorption bands are. Now, this doesn't mean this is because of the water in the plant. This means that there is no signal transmitted through the atmosphere because the water in the atmosphere absorbs everything. Understanding the difference between reflectance, what gets bounced back, absorption, what is consumed by the target, and transmittance, which is what goes through it, and how they combine to equal 100% of all the energy that was cast upon an object, and the wavelength where these particular changes between these three fields occur. So here we got leaf and we got water, and so vegetation reflectance compared to water absorption. You can see that there's certain places where they track closely, and other places they are wildly different. How can we use this? Well, we can look at plants, and as they become in having more moisture stress, the composition internally of the leaf structures begin to change because of lower levels of water, and that changes dynamically how we can see patterns. Coniferous versus deciduous. This one earlier, here you can see an example of aspens versus black spruce. Soils are not very diagnostic of soil type, the pigments anyway. The main controls over this reflectance is the amount of moisture and the organic matter content. Moisture makes everything look darker. It also absorbs more in the infrareds, and organic matter is a darker color, and so it absorbs a lot more of the visible light. Iron tends to give things a red to orange color, and so there's certain parts there that will respond. When you get to the 2.2 micrometer region in the electromagnetic spectrum, certain clays will exhibit a signature. All these are helpful in identifying soil. And so here you can see how the soil moisture content reflects how the changes in soil moisture affects the reflectance or the response to energy. So the lines at the top have very little water, the ones at the bottom have more water, and as you go from one wavelength up across the spectrum, you can see how more or less gets reflected. You can also see where the water absorption bands are, and that hydroxyl or that clay absorption band as well. So how does organic matter content affect reflectance? When you have very little, you reflect a lot. When you have a lot more organic matter, you reflect a whole bunch less. Iron oxides, organic matter, and soils. These are basically treatments where they've taken the soil and did things to enhance or eliminate some of this stuff, or to clearly identify it. In this example, what we're looking at here is we have the native soils with no treatment, and we have one where we remove the iron, and we have one where we remove the organic matter, and you can see how that made a distinct difference in the spectral signature or the reflectance. Summary: soils are dull in color. Organic matter lowers reflectance, especially in the visible. Water lowers overall reflectance. Irons boost the red. Clay creates absorption features at 2.2. Finer texture soils have brighter reflectance. We often have to go in and reference our data. We use ground truth it. It's not always on the ground though. Sometimes we use GPS. Sometimes we check it at a higher resolution to explain or clarify what we're seeing with our remote sensing. We use a lot of GPS and other such things. GPS has 24 satellites. GLONASS has 24. Compass is a new one. It's going to have 30 when it's done. Galileo will have 30 as well. So what are some of the errors that we come across in global navigation satellite systems, and how do we correct them? Interference from the atmosphere, the quality of the clock. We have various augmentation systems, and we have differential correction systems. One of the most common systems is the Wide Area Augmentation System, or WAAS. I want to talk just a little bit about cameras. That focal length is the distance between the lens and the object, the distance between the lens and the photoplane or whatever. Exposure is based on the brightness and time, geometric factors and exposure. Exposure is lessened as you move away from the focal point. Distance longer at the edges than at the center. What does that mean? Lenses are curved. When you look straight down on something, there's a certain distance. As you look to the edges of the available image space, the distance from your eye, if you will, to that object is longer than the distance straight down to the focal point or the center of the image. Dates on early photography. Likely that I wouldn't give you anything that quite specific. But you should know that they started collecting for the USDA around the Dust Bowl time because it was important. By World War II, we were using stereoscopic photographs. By 1990, we had digital cameras for civilian use. And by 2000, we had digital aerial platforms that were in widespread use. So how do you take photos from a plane? Well, you gotta get in a plane. And then you're going to follow along, and you can see that from the plane you're going to look at a principal point, which is straight down, and then there's a certain distance that you can actually encompass in the photo. Sometimes we have low obliques, that's like this, they're basically at an angle. We also have high obliques like this. It's an angle where you can see the horizon. Plane flies follows a flight strip. The idea is that this nadir line, basically the collection of the center points of the images, and each image overlaps significantly in lap. This allows us to have some stereoscopic stuff, and typically we try to take enough pictures that we actually have some portion of the data where we have 3 images. And then we line them up from side to side with side lap as well, so that we can get 100% coverage of everywhere with at least 2 images. We'll put them together, it looks kind of like that. Top one, high oblique. Bottom, low oblique. Panachromatic film. All visible light. It's sensitive to it. Black and white aerial photography. Typical panachromatic or infrared sensitive film. What is the difference? If you look at the infrared film, it goes out further. It collects into the infrared, whereas the panachromatic stops just past red. Color infrared film, blue becomes green, green becomes red, red becomes near infrared. It did it in World War II because things that looked like vegetation that weren't vegetation stuck out like a sore thumb with this particular kind of film. Filters become selective about what we allow to reach the sensor or the film. Absorption filters are the most common type. These absorb a range of frequencies based on color. You can also have polarized filters that can be used to reduce glare, incoming light sort of going in all different directions. You think about that wave, the individual peaks and valleys, and how it's moving. The high points are every so often, and that's your frequency, but it's not just in an up and down fashion. Those waves and peaks and valleys are in a 360-degree arrangement, but polarizing filters only let light through in one direction, so it makes it more like you see coming out the back of the illustration. Okay, reflection versus transmission. Here's what reflection means. Reflection means the color is bouncing off. When it bounces off, it makes things look red. Red objects absorb green and blue light. It makes them look red because the red is bouncing off. When we talk about transmission, red filters absorb green and blue light. They look red, but that's in part because the red is going through them. Photogrammetry is a science and technology of obtaining spatial measurements and other geometrically reliable products from photographs. In the old days, where they used actual printed photos, they called it hard copy. The modern digital version, we call that soft copy. It was once the standard procedure for processing photos, and now pretty much everything's digital and automated. Same process occurs whether you're looking at hard copy or soft copy. We just do it electronically, but you need to understand the theory of sort of how it works. So, a couple areas. First one is determining scale of a vertical photograph and estimating horizontal ground distances made from measurements on a vertical photograph. Scale is a mathematical relationship between distance on the ground and distance in the air. Range of scale is related to changes in elevation. If scale is known, it's pretty easy to make a lot of measurements on the photos. The second one we look at here is using to calculate area measurements. It's still the same. If you know the scale units, you can figure out the distances, and if you have two distances, you can use it to figure out areas pretty similarly. Now the last one is relief displacement. In photographs that do not show true to 2D view of objects, the top of it is displaced in a vase. And this is what relief displacement is, and they lean away radially from the principal point. And I have some pictures here that will explain that a little bit better. We're going to determine object heights from relief displacement, and so while it is a form of distortion, we can utilize that distortion if we know the scale and some other things, how high we're flying and whatever, and we see how far that that image is leaning out. We can use some basic high school trigonometry to run through and figure out how tall something is. Works kind of like this. You're measuring the height of a shadow, and you know exactly how high the plane is, and you know exactly how far something is from the principal point, and you can begin to figure out, if you know how far it is to the point, you know how far from the central point. If you know the distance from the principal point to the base of the object and to the tip of the shadow, and you know the height of the airplane, you effectively know everything that you need to know. You know the angle at 90 degrees. You know the height, or the length rather, of those two distances on the bottom. That means you know that entire length. And you can work through a lot of this and figure out various different things from time to time, and ultimately when you do all the proofs and whatnot, you can come up and say, yeah, that's this tall. And so we can also use this for terrain, and we can do it by using something called parallax. Parallax is the difference in the apparent position of an object viewed along two different lines of sight. It's measured as an angle between the semi-angle of inclination between the two lines. Like this. So the stuff I was talking about over there earlier about measuring. Now you got two images and you start to do this. It makes it a lot more difficult to not have enough measurements, not have the things that you need. Ultimately you can, by having two images and you see what the difference is, and you know the two different positions, as you start populating more and more distances and angles, the proving and calculating of how far or how high something is becomes a lot easier. The other thing we look at is exterior orientation. Production of maps is something that we do in DEMs and orthophotos. So if you're not sure exactly what this is, traditional hard copy stereo pairs, they use them to get a lot of distance calculations and stuff. We also use a lot of this information to generate an undistorted image, in other words, an orthophotograph. In orthophotograph, every pixel appears as if you're directly over top of that pixel looking straight down, and so you have no radial displacement, none of that kind of stuff. To do this, you got to figure out your flight plan, where you're going to go. You got to know all these other things that you're trying to do, and then you got to figure out, stuff like your focal length, your image overlap, your flight height, your distance between image centers, how many things you're going to take, what's the format of your camera. There's a lot of stuff that goes into it. What are the basic geometric characteristics that we're looking at? Vertical or oblique. That's virtually no vertical. We only correct it using a lot of simple techniques to get minimal amounts of errors. From that, we can generate digital models. We don't really have any loss of accuracy. We have different types of obliques like highs and lows. High oblique, you get to see the horizon. A low oblique, you do not. Here's a nice illustration of the nadir line, how much minimum overlap we have, and all that. And here we're talking about some of that stuff. You know the size of your sensor, you know the size of the target on the ground, you know where your lens is at, and you can really start to measure some interesting things. Just another way of looking at it. Ground coverage and aerial measurements, it's a function of a lot of things: camera format, focal length, flight height. It's dependent on devices used to measure the image, image scale variation, all kinds of stuff. Talk about relief displacement of vertical features earlier. You can see the shadows moving away, which would be telling of a lot of things, but you can also notice how the dark center in the middle of the cooling tower is not actually in the center, it's off to the side, because the principal point is sort of between these two and to the left of this image, and so they are displaced ever so slightly away from it. Kind of like this. We call that parallax. It's when you have an apparent change in the relative position of a stationary object. So you take aerial photos from multiple places, and you find two images where it looks like something has moved, but it hasn't. The only thing that's moved is you, and you can use that to calculate all kinds of stuff. Now you have to worry a little bit about your flight path, and you can see how it can get kind of crooked because you have to know exactly where the center of the image is. You need to know the direction that you're flying in, how your plane's tilted, and all that kind of stuff in order to get this to work. Here is a nice image of what parallax looks like in a practical sense. Same object, two images. One, the cooling towers are radially displaced slightly to the right, and the other, they are extremely radially displaced to the left. And so this would be an example of parallax. Orthophotos, no scale, relief, or tilt distortions. They're basically photo maps. Multi-ray photogrammetry, photomapping that exploits large numbers of mutually overlapping images simultaneously. Up to 80 to 90% overlap, it increases accuracy and facilitates near total automation. If you have enough closely aligned images that you can use multiple ones to get measures of angles and heights and whatnots, it makes the processing intense, but near perfect results in real time very quickly using computers especially. And so you can get some idea of how the more you have, the more different measurements you have, the easier it is to figure out what's going on. Talking about elevation displacement. So this is similar to all the other ones, but objects that are a little bit higher may appear to have a much greater displacement than objects that are maybe a little bit lower. But again, parallax can help this out. Tangential scale distortion is also a big one. As a rotating scanner, or a whisk broom scanner, if you will, goes from side to side, the area on the ground that is represented by an individual pixel at the airplane level is larger along the sides than it is directly straight down. This distortion is called tangential scale distortion. And you can see some examples of it here. Digital image analysis, just want to hit a couple of high points about this. How we do electronic imaging? The trend is to get away from film and go to digital. Consumers use it. Government stopped making hard photos in 2004. Storage is cheap. Maybe it will, maybe it won't last as long. It's really hard to tell. Digital format is computer capable. It also allows us a much greater range of sensitivity in terms of bright to dark. It's easier to calibrate. Electronic sensors typically have a linear response, where film has a log linear response, and only for certain ranges. We have a rapid turnaround time. We can actually sometimes look at our data literally as we're collecting it. Lots of different kinds of scanners. We'll discuss them in some detail later. Everything as simple as cameras to video cameras to camera arrays to push brooms or to whisk broom scanners. Advantages, it's very cheap, and you can record an audio track with a video, and so you can say things and make notes as you're doing it. However, because it is continuous, it's kind of difficult to work with in the view, and you don't always have as good a spatial resolution. That's the problems with aerial videography, or it's aerial videos. Small format photography is another kettle of fish. It's a cheap method to acquire your own data, and the only thing that you really got to pay for is an airplane. or a helicopter. You have total control over when you're collecting it and how you're collecting it, and the resolution and the flight height and all that. You just need some means of mounting your camera and then collecting your georeferenceable images. Once you have a bunch of images, you can then create a mosaic. In other words, you line them up and put them together, and then there you go. One big aerial photo of the place where you only had limited number of pictures before. I want to talk about how cameras work. Standard digital camera chip has something called a Bayer array. It does not measure the red, the green, and the blue the way you think it does. It has sensors for red, it has sensors for green, it has sensors for blue. It has more sensors for green than anything else. It has fewer sensors for red than anything else. It then takes the few sensors that it has and does a spatial interpolation to fill in all the blanks. The same thing happens with the green, the same thing happens with the blue. Once you have a red, a green, and a blue, then those images are combined to give you the true color image. So every pixel has 3 sensors and a Foveon chip. The uppermost sensor transmits light to the lower sensors. This eliminates this interpolation. And so basically the number of sensors is a 3x of the array size. So if it's 100 by 100, it's really 100 by 100 times 3. Here are some examples of some different systems, just some photos. An image, you can see what you might get with something like that. We have an array camera. It's multiple single band cameras, each filtered to a specific wavelength, and the idea is that you might have 3 to 8 cameras, maybe more. Each one is set up to target a specific wave length that you're interested in, and then you can combine them all together to have this multispectral data set that you want. Usually they're spatially registered to form what we call a multispectral stack. However, you can have registration problems when you do this. Here's what an old aerial photography setup might have looked like. One of a more modern setup is something called a push broom sensor. Here we have 4 multispectral bands, 8 charge coupled devices per line, or 8 charge coupled device lines. Each one has, excuse me, 12,000 pixels. And we can use this to do panachromatic stuff or any kind of photogrammetry with nadir or images, or off nadir imagery, things up to 16 degrees backward. So why do we use electromechanical sensors? If we look at the spectral range, film is limited, sensors is broad. If we look at the number of bands, film is broad, sensors are flexible. Film, 1 to 3, sensors, over 200. Calibration, nearly impossible, very doable. Radiometric responses, non-linear and limited, linear and over a wide range. One, you have to have film, the other, you just need electricity. One needs communication, you got to send it somewhere, tell them what you want, all the other is in digital, so it's much easier to maneuver around. What are the elements of resolution? I mentioned it before about the principal point being where you look straight down from the camera to the ground. This gives us something called an instantaneous field of view. That is literally, if you're looking down from that sensor or the camera, either one, however you want to think about it, the total area on the ground that you see, it's kind of an instantaneous field of view. Now here we're looking at it on a pixel basis. So from a single pixel from a sensor, an electromagnetic array, it too has a field of view, how wide an area it's going to measure, and when it gets to the ground, that's what it samples, and that corresponds to a pixel. So I jumped around there. I'm not sure if that's going to screw up the lecture or not, but we'll see. Pixel size is more or less the same thing as resolution, but for an object the same size as a pixel to be seen, it's a problem, because more than likely it's not in a pixel, it's likely going to be in parts of 4 pixels. This is a phenomenon we call mixed pixels. What it means is, if you have a 3 meter resolution raster, 3 meter pixels, and you're looking for an object that is 3 meters on the ground to show up in your remote sense data, the only way that really works is if your 3 meter object is directly in line with the grid spacing of your 3 meter grid. If it's off, then by one means or another we're going to calculate what we believe each of those pixels to be, and with only part of that object in them, it may or may not register as that particular thing. In general, to be visible, objects need to be twice the dimensions of pixels. That way you're likely to need at least one pure pixel. Resolution is also determined by a lot of things like the contrast ratio between the object and the background. Small, very bright objects on a dark background are easy to see. Large objects on a similar background are also relatively easy to see. But the other side of that, small, very bright objects on a bright background, no. Large objects or small objects similar to the background, no. So we talked a bit about a whisk broom scanner. It's also sometimes called a cross track, and the way it works is the scanner has a rotating mirror that takes the sensor and it collects information on a cross back and forth path, just like you would run a whisk broom. Here's how that kind of works. You got this rotating mirror, spins everything, goes through the various sensors, sends that information up, splits it apart to the various detectors, goes into the electronics, and then it's ultimately recorded. And a long track or push broom scanner is a little bit different. Instead of having a single sensor that is constantly getting feedback and then recording it and then moving on to the next sort of cell in the grid, if you will, a long track or push broom scanners have an array that is a set size, and it measures a set size swath on the ground, and as the plane moves forward, the direction of motion, it moves on to the next set of measurements. So let's compare some sensors. Whisk broom, short dwell time to collect photons, moving parts, problems, fewer detectors. Push broom, each array has its own band, has a longer dwell time with a lot of detectors. You get a better signal to noise ratio, you can calibrate between detectors, not as many moving parts, uses less energy. Here you can kind of see sort of the evolution of how these compare to each other. Aircraft versus satellites, which one do you want to use? Here's the reasons why. This is getting us a fair way through. When we look at image interpretation, trying to figure out what things are, shape matters. Certain shapes are unique, things that we don't typically see, that we know are man-made, that make us think about what it might be. Things like an airplane or a pentagon are shapes that we can go, yeah, that's not normal. You can also look at shadow. Shadow reduction is of concern in remote sensing because shadows tend to obscure objects that might be otherwise detected. Sometimes the shadow of an object is the only thing that helps us really figure out what it is. So they can help or they can hurt. They can be qualitative or quantitative. And here you can see the top one, the radially displaced shadow of a water tower. On the left you can see the radially displaced shadow of pyramids. And similarly you can see the shadows, how they're going on the overhead of the trucks there on the highway. Another thing we talk about is tone and color. A band of electromagnetic radiation recorded by a remote sensing instrument can be displayed on an image in shades of gray ranging from completely black to completely white. We call those tones. We have the ability to see about 40 to 50 tones. Tone is related to the amount of light reflected from a specific wavelength interval. And so color and tone, we can see how depending on which ones you select, you get very different looking stuff, and it makes it very much less challenging to identify where the unique and interesting things are. Another thing we look at is texture. This is the arrangement of tone and color in an image. This is important because Earth features that exhibit similar tones often exhibit different textures, and so we can use this to help figure out what's what. The typical adjectives we use with texture are things like smooth, which means it's sort of uniform, intermediate, or rough. So here we have some different textures in the imagery. We also look a lot for patterns. We don't really need a software to find patterns. We have the best pattern detection algorithms ever evolved, and they are our own in our eyes, in our minds. They help us, or have helped us in the past, not to become victims of hungry wild animals or other humans with ill intention. In general, descriptions include random and systematic, natural and man-made elements in these patterns. More specific descriptions include things that are like we would call something circular or oval or curvilinear, linear. All these are describing how things are. And on the top here we see this pattern of roads and housing developments. In the bottom left we see a really interesting pattern because of parked planes. In the bottom right we see the dendritic patterns of a delta. We also look at height and depth, and a lot of this comes from shadows, and we use it to figure out what's going on. Association is very important when trying to interpret an object. Association refers to the fact that certain features or activities are almost always relative to the presence of certain other features or activities. In other words, you typically see certain things together with other things. Very different things, but things that go together like airplanes and runways. So here we have 3 images, and if we look at the one on the left, we see we've got some cooling towers or some smokestacks or something, and we've got some various ponds around, and we've got some round things, but they're probably petroleum tankers, and so this is likely some sort of a petroleum fuel processing location. Similarly, on the right, or the center, but to the right of the first image, you see stacks of timber and various things going on there as well. And then all the way to the far right, you got a cooling tower, which makes you think it's likely a power plant of some variety. And then if you could place it spatially and things, you'd be able to figure out where or what it actually is. So now that you've got all those ways of collecting this information, how do we do something with it? Well, we can spot patterns real easy. Spatial patterns, we look at changes in shape and size and the context, and spectral patterns, where we look at things that are darker or brighter and in different colors. We can use remote sensing. It's usually spectral only, where each pixel gets classified independently. We do this to then figure out what all we can do. So how? Supervised and unsupervised classification are the 2 primary means of utilizing information like this. So how do we do that? First thing we gotta do is pre-processing. Why? Because if we don't correct the geometric issues, where there's no distortions and have things georeferenced and properly projected, they won't line up and it'll make things what we like to call wrong. As far as radiometric corrections, there's systemic errors and brightness variations, that kind of stuff. If we're going to try to make real numbers out of it, that's more of a problem, but for some uses this isn't going to be a big deal. Why do we have to worry about all this stuff? What if we're looking across multiple days? Then different amounts of sunlight need to be considered, or we need to pick methods of analysis that will not be messed up because of that. We also got to look at light, hillshade, topography, and all that kind of stuff. Ultimately, we'll end up with geometrically correct georeferenced images, in other words, ortho rectification of images, or digital elevation models. That's all you really need to create an ortho photo. We can use our image analysis to look at contrast and brightness and transparency and gamma, all these other things to compare properties. We can use our various filters. Low versus high. Low smooths things, high enhances things. We can look at focal statistics and see how the overall values change across an entire image. Things like the float tool and the band tool and map algebra all give us a means of processing this data. So as far as image processing, we do things like correct distortions, calibrate, mosaic, and it's all the pre-processing steps. The image enhancement is basically a means of creating information. The image classification helps us identify clusters and patterns, whether we use supervised or unsupervised. And then the other thing we look at is sort of self-explanatory. We look at changes and stuff and see how the images have changed or the data has changed over time. Data fusion and GIS integration is basically fancy, kitschy kind of words for combining data sources or times. Hyperspectral data, when we talk about that with image analysis, that's where the real money is made, if you will. That's where we take all kinds of information to find things out. Biophysical, things like estimating the number of people at an event, things like that. So what are some of the pre-processing steps we might want to consider? Noise removal, de-stripping line drops, and getting rid of random noise. Radiometrically, what are they? Well, the sun's not always the same brightness or the same distance from the Earth at different times of the day. When satellites pass over, we have to take into consideration whether those changes will impact our analysis or our location that we're analyzing, and then decide whether or not we need to address those or not. Geometric correction. A lot of raw images have geometric distortions, so you need to be cognizant of stuff like the instantaneous field of view, where nadir's at, whether you're looking at data from a push brim or a side sweep, and use this to your advantage when you're repositioning things. Subsetting, layer stacking, mosaicing, reduce data volumes. It combines bands or combinations. You can group nearby things together and mosaic them. We're talking about stretching. Here's the equation for it. Convolution, smoothing things out, how it blurs the stuff around, has a sort of moving window, and it softens up edges. Edge enhancement. Sorry for that pause there. Opposite of convolution. So in convolution, we're smoothing things out. With edge enhancement, we're looking for things where there's dramatic and quick and abrupt changes, and we're doing things to make those quick and abrupt changes more obvious. And that's basically all it is. Multi-image manipulation Spatial ratioing is a way of doing this. And so I read somewhere once that think of it as grades, not points. It doesn't matter what your value is from image to image. You're comparing one value in an image to another value in an image. And so you get some ratio, some percent. And so you're comparing the grades, the percent on one photo to the percent on the other photo, as opposed to the actual measured numbers on each one. And we use this as a means of creating these various indices like the NDVI, the SAVI, the GNDVI. And for example, the SAVI is the submerged aquatic vegetation indices. So what are the different methods of remote sensing classification? Well, first let's look at this quote here. You can fool some of the bands all the time, and you can fool all the bands some of the time, but you can't fool all the bands all the time. In other words, things that are different will in some fashion or another look different sooner or later to where you can separate and identify what they are. So we have our remote sensed data. Whether we let software do it or whether we do it ourselves, ultimately, ultimately we are selecting, I think this is this and I think that is that. And then based on those two populations, the software will assign a boundary between the two, and things that are more like one or less like the other get assigned accordingly. Two approaches: supervised, unsupervised. In supervised, you have to identify representative training sites for every class of stuff that you want to identify. It then generates these decision boundaries. In unsupervised, it uses a cluster algorithm to figure out where these clusters are, and then you have to go in and decide and label what those clusters are. The process works like this. In supervised, you identify training areas, algorithm identifies the signatures, and it classifies all the pixels and then generates a map. Unsupervised, it identifies clusters, finds the inherent classes, classifies everything on those clusters, and again gives you a spectral class map. You have to go in and then label them. Sometimes that involves grouping them together, and then ultimately you end up with an informational class map. How do we label them? We can do things like bispectral spots or spectral curves, or we can create classification maps. So how do spectral classes versus informational classes differ? Well, in a perfect world, if it's a spectral class A, it's an informational class. Just that simple. In reality, a lot of times you'll have multiple classes that are the exact same thing, or you'll have classes that are actually different things, and you'll have multiple classes that are different things, and it can get complicated because of stuff like this. Old asphalt versus new asphalt look like very different colors. So you have to really do a good job when you're classifying things or providing training or assigning and grouping the classes that the software already chose. It's not as easy as it might look. Unsupervised methods: histogram, peak and valley finding, and ISO data moving means are some examples. Histogram valley finding is pretty easy. With histogram valley finding, we look at the histogram of our DN values relative to the frequency, in other words, how close they occur, and we'll have lows and highs, and the idea is that the more something occurs, the more likely it is something, and the less likely something occurs, the less likely that it is anything significant. And so in an example like this, you would simply pick that low spot there and divide that up, and everything on one side would be in one class, and everything on the other side would be in the other. The problem we run into is stuff like this. It doesn't work quite so easy. That's where we use the ISO data technique. It is an iterative self-organizing data analysis technique, a lot more robust. You specify the number of iterations, the maximum number, the minimum changes, and all that kind of stuff. It looks at the clusters. It generally finds less than what you'd say is the maximum. and then it works. And it does this using principal components. In other words, it uses statistical analysis. And it splits and merges based on the parameters, some of the stuff that you set. Ultimately, then, it works through and continues to try to improve the classes until it thinks they're best. So here's an example of this bispectral data plot that we might use in an ISO data classification scenario. And so it identifies clusters, and they might be arbitrary. And it goes from there. It assigns those clusters, and then it measures the statistical properties of those clusters and tries to decide whether there's things in those clusters that need to be kicked out, if there's things in those clusters that need to be added in. Every time it does this, the mean changes ever so slightly, and then it begins to do this again differently. And it continues on and on and on, repeating the process multiple times until it doesn't really see much change. At that point, it stops. In supervised, we go through this how to represent the training class data. You can use actual distributions, but that's not very efficient. You need to generalize. You can use summary statistics. And supervised minimum distance is sort of one technique where it looks at these various clusters, and then it says, okay, which one am I closest to? And that's kind of where it tries to fit everything. Problem is sometimes you might be closer to one and still inside that population bubble of the other. So by not looking at the variance of each class, it's not really the best option, because you end up with a class break that looks something like the purple lines as opposed to the variance of the data that you see in the color shapes around the other letters. Parallelopeds are just another means of doing that, but again, you see you get some overlap, and so if you get a lot of correlation between your data, it's a problem. Bayesian likelihood system is kind of maybe a little better option to go through, trying to find out what is my most likely group I belong to. Probability density contours is another. Here we have these classes of things, and the spikes indicate the increased numbers of things that's going on that tell us, ooh, this is a class. The areas where we don't see a lot of that, it becomes very flat, and so we can then draw lines around the flat places between the peaks, and that helps us create the boundaries of what becomes the urban or what becomes corn or water. After we do classification, we have to evaluate everything. Subjective evaluation, does it look right? We can look at our confidence as well. We can look at our accuracy assessments and look at the statistical sample and test it for accuracy. There's lots of different ways to do it. Again, just remember that classification is iterative. You got to add and delete and merge your various signatures and stuff to get things to ultimately work out. So that gets us down to kind of our last hurrah before this midterm exam, change detection. And so I'm going to go through parts of this pretty quickly, and then there's a couple things that I didn't do a very good job explaining, and I'm going to try to do a better job today. Digital change detection. It's a biophysical materials and human man-made features are dynamic and changing rapidly. So land use and land change is a major component of global change and impact that could be even greater than climate change, because we just fundamentally change the biochemical makeup of the planet. And so we've done a lot of effort to develop change detection methods that work from remote sense data. We had a tsunami in 2004. Excuse me, it significantly impacted certain areas. This is one of them. We can look at imagery before and imagery after, and we can see areas where there was once a wonderful beach and some light forest and some urban development, and then now it has literally stripped all the vegetation from the earth, leaving it barren and free of vegetation. It's a pretty significant change. So successful remote sensing change detection requires a lot of attention to things like the sensor considerations and the environmental characteristics of what you're looking at. Ideally, remote sense data used to perform change detection is acquired by a remote sensing system that holds all resolutions constant. In other words, the data quality is the same, the data variability is the same, and everything just basically is the same. And so when things are different, you know it's a change. Temporal, spatial, and look angle, spectral, and radiometric are all different types of variability that we can try or want to try to hold constant when we're doing this kind of work. Temporal resolution should be held constant during change detection if we can do it. Ideally, the same sensor that we use on one date we use on the other, so that we have the same spectral information. Radiometrically, same precision on both dates. And spatially, we want everything that we collect have the same instantaneous field of view on each date. Use minimum mapping units, use a consistent look angle, and we want our registration to be very good. As far as the results, radiometric results refer to how much information is in a pixel. So when we talk about radiometric resolution, that's 8-bit, 16-bit, 24-bit. And the thing that you need to remember is, if you're looking at data that is a different bit from one to the other, there's more information in one, there is another, there's more classes in one, there is the other. It makes it incredibly difficult to combine that data to some usable end. Everything should be geometrically rectified. In other words, not just that it's georeferenced, but that all the images that you're working on, all layers, all the data sets, that they are as close to 100% perfectly aligned as possible. Why do we rectify? Everything needs to line up for change detection. To detect change, you must align exact locations with each other. You got to make sure that a change is a change and not just a poor registration. Remote sensing environmental considerations of importance when conducting change detection. If you don't understand the various environmental conditions, it can make it really hard, and you can get a lot of really inaccurate, screwy results. You want to hold as many environmental variables fixed as you can. Things like soil moisture. Wet ground versus dry ground makes a lot of things look differently. Vegetation that grows according to relatively predictable cycles. And so things that you collect in the spring look often differently than things you collect in the fall or the winter. So you need to try to be cognizant of that, and then depending on what you're looking at and where you're looking, you want to do your best to collect images that are free of all these seasonal and phenological changes that will identify change that doesn't necessarily exist. You want to just try to get the best matched conditions. Moisture. Wet dirt looks different than dry dirt. So, significant changes in moisture change color. More moisture, better response to some bands. Infrared, near infrared particularly. Alters the spectral signal. Vegetation. Different trees are different colors of green, believe it or not. Different trees have different kind of needles. Different needles respond differently across the electromagnetic frequency. Not all needles are the same. Not all needles are the same color. So when we talk about vegetation, are all leaves the same? Do all trees respond the same? Are all evergreens the same? Are all needles the same? When you look at things like changes in moisture or season, it might expose something in an understory or another condition that you wouldn't otherwise see. I want to point out something there in that last bullet. There's tons of little mistakes there. And part of that is I have a wireless keyboard and I think the battery's going dead, and it's not always putting in all the keystrokes that I hit. That's what's giving me fits trying to make this video. Leaves, different shapes, different colors. Leaves, same shape, different colors. Again, to see how we can have problems. How did it select the best change detection algorithm? Now, this is the confusing part that I just did a terrible job trying to explain in the original class slides. So, change detection algorithms typically use a post-classification comparison. What does that mean? That means we classify the image first, and then we compare changes in the individual classes. Another thing we do a lot is multi-date composite images and principal component analysis, as well as image algebra and change vector analysis and binary mask. So let's look at a couple of these and see if I can explain them a little better. Post-classification comparison change detection requires rectification and classification of each remotely sensed image. What does that mean? Okay. Step 1, rectify the two images so they line up as perfectly as possible so that there's not differences in values because the images aren't lined up. Step 2, classify both of the images according to a list of land uses or land covers or whatever, however you're classifying it out, and use the same classification scheme on both images. Two maps are then compared pixel by pixel, looking for, this is not the same as what that was. Every error in the individual class map can also be presented in the final change detection map. And the individual classification maps are used in a post-classification change detection have to be as accurate as possible. Alright, so here's their idea of what a post-classification comparison change detection looks like. You have data from two different dates and time. You have multiple bands at one date, and you use this to somehow come together to generate a classification map for the first date. You do the exact same process for date number 2 with the data from the second date, and then you ultimately convert that into, or you compare that then to the classification map from date 1. And then you look at the difference between date 1 and date 2. Here's Hurricane Katrina before and after, and you can look at the changes. And just looking offhand, it's really hard to see much going on there. So, change detection algorithms commonly used include post-classification comparison, multi-date composite, principal component, image change, we already went through these, binary mask, etc. So what does multiple date composite image change detection look like? Here we have two different dates of Iconos. We can go to a traditional sort of classification approach, or we can look at principal components. And principal component analysis is just a statistical analysis that looks at the variability across multiple parameters, and it creates a new variant, in other words, like a regression equation that explains significant parts of your data. So you rectify all the images. This composite data set can be analyzed to extract change information. Unsupervised classification techniques will result in the creation of change and no change clusters. And then you have to label the clusters accordingly. So you end up with something like this. Multiple date composite image change detection, principal components. Comes up with the ones here, and you see 2 is a good indicator of changes between the images, and so that's the one that we're going to look at. Another technique is called image algebra change detection, and you identify the change between 2 rectified images by band ratioing or image differencing. Image differencing involves subtracting the imagery from one date from that of another. If the two images have almost identical radiometric characteristics, the subtraction results in a positive or negative value in areas of radiance change and zero value in areas of no change. And then everything is stored in this change image. So how does image algebra change detection look? Let's start with date 1, 3 bands, date 2, 3 bands. You then generate composite data sets, and that would be, for example, what if we looked at a ratio of band 2 to band 3, and we did that for date 2. What's the ratio of band 2 to band 3? And we get these two ratioed bands or composites, and we then simply look at the difference. Then we apply a threshold of how different does it have to be a difference, and that gives us our results. Now, when we talked about how different has to be, if it's the same, it's a 0. If it goes more one way, it becomes positive. More the other way, it becomes negative. You can fit out a histogram. If you can fit out a histogram, you can apply some basic statistical foundations to it. Know that at a certain point, as you move a certain number of standard deviations away from the mean, the probability that you are no longer part of the same data set, that you are in effect something different, unique, and new, comes into play, and that turns out to be a really good spot where you can say, yeah, at this point it's changed. The variability that we see less than this or greater than this is likely just a variability that was within the data set to begin with. But when the change becomes this extreme, it is likely actual change. And so how do we do that? Principal components is a tool we use to do this a lot. It takes these input bands and it can put them into a multivariate attribute space, into a new multivariate attribute space whose axes are rotated with respect to the original space. Well, that's a lot. Think of it like this. Take all the bands, do regression, come up with a linear combination that explains the majority of your data, and that's component 1. Next, you then create a new combination of components that explains the majority of the remaining data that is orthogonal to the first component, and so explains it in the other direction as much as possible, and so that becomes component number 2, and so on and so forth. And the idea is that you want to create these new variates, these new variables that are composite features that do not overlap or do not hit on the same targets. They counter one another. Alright, I think I've done that enough. I'm not going to talk about that. This maybe. Green line would be your principal component number 1. That is the linear combination of different bands that explains the overall variability in the data set as best we can. And then the remaining residual stuff that we see would be explained by the next component, number 2. And it is orthogonal or in the opposite direction. Cut and fill is another easy one. Common for mountaintop removal, elevation-based changes. Take a digital elevation model 2 different times, use map algebra, subtract one from the other. You get positive and negative values. Negative values is now a hole. In other words, somewhere you dug out, it's cut. Positive values is something that got filled in, that's fill.